Final video on how to do Bohr models. This one is about isotopes. So there's already been a video on how to do basic Bohr models. If you're looking for that, go back in the classroom. You'll find it in a different video. There's been one about how to do Bohrs with ions. Those are the charged guys, things with pluses or minuses on them. Go back in the classroom. There's a video on how to do this. This is Bohrs with isotopes. Because again, this time what we're doing is we're not changing the charge. We're not changing what element it is. All we're going to do is change the mass. And going to the table, the part that we care about then was just on mass. So mass, and we had proton, neutron, and electron. So this is explained back in the how to do Bohr models. So we're going to say protons have a mass of 1, neutrons have a mass of 1, and electrons we're going to lie and say that they have a mass of 0 because they're so small we can ignore them. So we're going to say they have a mass of 0, even though that is not true. Their mass is small enough where we can ignore them for these Bohr models. All right, so let's dive in. Like I said, you should already know how to do a Bohr model. So let's go to this guy, beryllium. You can see over here in the left side of your screen that beryllium is element number 4. So generic thing on how to do beryllium, they would have 4 protons, he would have 5 neutrons, and he would have 2 rings of electrons, 2 in the first, 2 in the second. And that's a generic Joe Schmo beryllium. And most of them do look like that. But sometimes when you look at that average and you see over here that its average is 9.0122, this guy only weighs 9. So that's the average of all the berylliums in the universe that we know about. And when we look at that, the average is a little bit higher, which means somewhere out there, rarely, but sometimes, there's a beryllium that must be a little fatter than this guy, a little heavier than this guy to bring that average up. And how we would show that in the symbol, this corner was for the charge, we would write a number over here. It's not going to have a plus or minus. So let's say we're looking at beryllium 10. Another way of writing that would be if you had beryllium, had to look to see if it had 2 L's or 1, beryllium dash 10. That's another way of writing it. I personally will always do this way, but this is also a way you can write an isotope's new mass. So if you were doing this guy, mass of the atom, as always, is protons plus neutrons, because those are the only guys that have any weight. We still cannot change the number of protons because that's what makes beryllium beryllium. Beryllium has 4 protons, always has, always will. So when beryllium had a weight of 9, then that was simple math. 4 plus 5 is 9, so normal beryllium has 5. But now that we have beryllium that weighs 10, still 4 protons, so now the neutrons is not 5, it's 6. So if I wanted to do a Bohr model of beryllium, what I would do, go to the periodic table and see that beryllium has 4 protons. Nothing changes with the electrons. Isotopes don't have a charge. Ions do. And it is possible for an atom to be an ion and an isotope. Nothing says it can't. But this guy's just an isotope. So what we are going to look at is this 10 right here. I'm not even going to look at the periodic table. You can and look over and go, normal dude is 9. Don't care. This guy is 10. So 4 plus neutrons is 10. So in this case, that's going to be 6. And that's literally all there is to the isotopes. Isotopes is just saying, if it gives you a mass here, don't use the periodic table mass. Don't do that decimal that you have to round. If it gives you a number here, use that. So let me give you one example on that. So if we do hydrogen, hydrogen's an easy one. So let's say I do hydrogen 3. This is a real isotope that exists in the universe, just like there's an H2, and there is my normal, everyday Joe Schmo hydrogen, which is H1. So what's the difference between hydrogen 1, 2, and 3? Those of you, again, that like vocab, never need to memorize this. They call this guy right here protium. This guy is called deuterium. And this guy is called tritium. He's radioactive, but they're names. What I care about is the 1, 2, and 3 weights. So they're all hydrogens. So every one of them is going to have 1 proton, because that's what makes hydrogen hydrogen. But this guy has a weight of 1, so he must have 0 neutrons, because 1 plus 0 is 1. This guy's got a weight of 2, so he has 1 neutron. 1 plus 1 is 2. And this guy, he's going to have 2 neutrons. 1 plus 2 is 3. And that's all there is. That's how you do Bohr models with isotopes.